Okay, so in the last video we had a somewhat informal discussion of subdivision of chains. In this video we'll just go ahead and give formal definitions. So start by saying so iota n is the identity map delta n to delta n. So that's considered as an element of Sn delta n or of Cn delta n. So this is just kind of a basic n chain in the n simplex. And then we're going to define theta naught is the same as iota naught. Okay, so that's just an identity map from a point to itself. And then we're going to define theta n prime is the sum from I is 0 to n minus 1 to the power I okay. Okay, so then so theta n prime is going to be like this. We so we're supposing that we've already defined theta n minus 1, and we've got these maps delta I from the n minus 1 simplex into the n simplex, and using those we can push forward this theta n minus 1 to get a get an element n minus 1 chain in delta n. Then I'm going to put Bn Bn is going to be the barycenter of delta n. That's the point with coordinates 1 over n, 1 over n, 1 over n plus 1 in each slot. So that's just the midpoint of delta n in the obvious sense. Okay, and then there's beta. Okay, so this is going to be an operation we do on linear simplices. So we've got a linear simplex like this in delta n. Okay, so you've got just vertices A0 up to AR, and you fill them in an obvious way to get a R simplex in delta n. So beta of that is what you get by just putting this barycenter at the beginning. So you take the simplex wherever it is, and you connect it to the middle. So this is what we do for a single simplex, and then we extend that linearly in the usual sort of way. Okay, and now we're going to define theta n to be beta of theta dashed n. Okay. So in other words, we take do this prescription here to get this this element. So this notice here this has gone up by 1 dimension because you added an extra thing. Okay, so here we had our theta n prime. That was a n minus 1 chain in delta n. We connect everything up to the midpoint, which bumps up the dimension by 1. So this guy here is in Cn delta n. Okay, so now this is an inductive procedure which defines theta n for all n. Okay, and then finally, given some u from delta n to x, we define the subdivision of U to be what we get by applying U hash to theta n. So that's in Cnx. Okay, so this defines our subdivision operation, and well, there's a bunch of things we need to check about its properties. Okay, so so one kind of obvious property is that we could ask what's the subdivision of iota n. Well, remember iota n was that's just the name for the identity map on delta n. So here we're just applying the identity map to theta n, but that doesn't do anything. Of course, so that gives you theta n. Okay. So we define subdivision in terms of theta, but equally we can define theta in terms of subdivision. That turns out to be useful. Okay, so now next property I want to mention is so-called naturality. So suppose I've got some function f from x to y and some u from delta n to x, then there's two things I could do. I mean, firstly, so this is a basis element in Cnx, and then I could push it forward to get a chain in Y. But remember, what the definite f hash u is that's just the composite of f with u. Okay, so this is take f composed with u, and we push forward theta n according to this. But this kind of push forward of chains is this is functorial. So that's the same thing as f hash of u hash of theta n, which is f hash of the subdivision of u. So if you like, we can express this as a commutative diagram. You've got Cn of x. You push forward to get to Cn of y, and then you subdivide to get to Cn of y again. But that's the same thing as doing the subdivision first, and then pushing forward. Okay, so that's going to be a useful property as well. And the third thing, so what's the subdivision of the boundary of the identity simplex? Okay. Well, the boundary of the identity simplex is the alternating sum of these face maps delta I, right? I mean, here we're kind of thinking of delta I. That's the inclusion, one of the face inclusions here. So we can think of this as being an n-1 simplex in delta n, if you want. Okay, so and then the boundary of iota n is just the alternating sum of these. Okay. And then the subdivision is by definition, it's defined to be a homomorphism. So we get the alternating sum of the subdivision of delta I, but that's delta I hash of theta n minus 1. And this was, by definition, theta n prime. Okay, so let's just write it as a single equation. subdivision of the boundary of iota n is theta n prime. So, so I said, we define subdivision in terms of the thetas and theta dashes, but these equations are telling us that we can kind of go backwards. Once we've defined subdivision, the theta is just the subdivision of iota n, and the theta prime is the subdivision of the boundary of iota n. Okay, so another ingredient in all this group of definitions was this map beta. So let's just recall that. Okay, so beta, this was a map from linear simplices in delta n to linear R simplices to linear R plus 1 simplices, and it was defined by you've got a linear R simplex like this. Then you just put in beta n, the barycenter, Bn as the first vertex, and keep the rest of the vertices there. So this is just the operation, taking a linear simplex and joining it to the barycenter. So on this kind of chain homotopy type relation, I'm only going to prove this. I'm not going to say what happens in degree 0 because it's not useful for us. But in case of R is bigger than 0, I want to claim that if we do d beta u plus beta du, then that'll just be equal to u. And the proof's not very difficult. Okay, so I'm implicitly claiming this in a case where u might be a linear combination of terms like this, but it doesn't matter. We can just do it for a single term and it will all work through. Okay, so okay, so we take this thing, we take the boundary. Well, you firstly, the boundary of one of these guys, you just omit. You take, you omit one vertex each time and put in the appropriate sign. So we omit the Bn. That just gives us our A0 up to AR. Then you have a minus sign. You get the thing where you omit the A0. And then carry on, and then the last term is where you get your Bn, and then you get A0 all the way up to An minus 1, and the An is omitted. On the other hand, if we do beta of du, so that's beta of what now? So here we omit the A0, so you get A1. Then you get minus the thing with the A1 omitted. And then the last term. Okay, that should be an R minus 1 here. Okay, so right, so you get to all these terms like this, and then you do beta to this, which means you just put the B0 in. So the Bn, right? Okay, and now you see, we'll see, you've got this term here with a minus sign. It's going to cancel out against this term here with a plus sign. Right? And similarly, the next term here will have a plus sign, or we'll cancel out this one, which has the minus sign, and so on. And then this one here, this one, actually we could be a bit more precise. This one is going to be -1. So this was this r is here is appearing in position r plus 1 because we put the bn in, so that's a -1 to the power r plus 1. And then this one here, this one, that's just in position, right? Here we're omitting the AR, which is in position R. So it comes with a power sign -1 to the R. And then here you're just doing B that doesn't change the sign. So that's a -1 to the R again. So again, you've got opposite signs here and here. So this guy is cancelling this guy. Okay. So everything cancels apart from this original term here, which was just equal to U. Okay. So yeah, we've got beta d plus d beta is the identity in degrees. Degrees strictly bigger than 0 anyway. Okay, so now the next main claim is we want to claim that this subdivision is a chamber. Okay, so we're claiming that if you've got any map U from delta n to x, then the subdivision of the boundary of U is the same thing as the boundary of the subdivision. I mean, in principle, we're claiming this actually if any linear combination of maps like this, but it'll be enough to check it for just one of them because then everything's a homomorphism. Okay, so that's a claim, and the proof's by induction on n. N is 0. So in case n equals 0, of course, there's nothing really to say. Both sides of this equation, they both lie in the in the 0 group, and so they're equal. Okay. So n greater than 0. Well, there's several things to do. So so we can assume that SDDV is DSDV for all V in Cn-1 of any space X. So what we're going to do is we're going to take V to be the boundary of iota n. So that's an element in Cn-1 delta n. So recall, on the other hand, so SD of V, that's SD of the boundary of iota n, and that was the element that we called theta n prime. Okay, we proved that a minute ago, that the subdivision of the boundary of iota n is theta n prime. So the claim is that if we take the boundary of theta n prime, that's the boundary of the subdivision of V. That's the same thing as the subdivision of the boundary of V, which is the subdivision. Now V, remember, was d iota n, so this is d squared iota n, but d squared is 0. So that's the subdivision of 0, which is 0. Okay. So the bound. Subdivision of the boundary of theta n prime is just 0. Okay, so now we're going to apply beta to this. Um, um, yeah. Okay, so now we've got this identity here that the boundary of beta theta prime n plus beta of d of theta prime n is going to be equal to theta prime n. Now, this term here, remember, is just, we've just shown that d theta prime n is 0, so this term here is 0, and beta of theta prime n, that by definition, that's theta n. Okay. So we conclude that the boundary of theta n is the same as theta prime n. Okay. Yeah, there's actually going to be a slight extra argument needed for the case of n equals 1, but okay, because this we only checked for in the case of stuff of degree strictly bigger than 0. Now here our theta prime n as degree n minus 1. So in the case n equals 1, this identity is not immediately true, but you can just check that case directly. It's a very simple case. Okay, so now we've got this fact here that the boundary of theta n is equal to theta prime n. Okay, so let's just write down again what we just proved. Boundary of theta n is theta prime n, and let's also remember the subdivision of the identity is theta n, subdivision of the boundary of the identity is theta n prime. Okay. Okay, so let's look at these equations here. So we've got the boundary of the subdivision of U. Okay, so that's the boundary. Well, if you remember, what's the definition of the subdivision of U? That was U hash of theta n. Okay, but remember these U hashes. These were U hash is a chain map. That's a kind of key property that we proved earlier. That whenever you've got a continuous map between spaces, it gives you a chain map between the corresponding chain complexes. So this U hash is a chain map. So this can be rewritten as U hash d theta n. Okay, but what's d theta n? Well, we've just checked here that it's equal to theta n prime. So that's U hash theta n prime. And now we need to remember what was the definition of theta n prime. So that's a U hash of sigma I is 0 to n minus 1 to the I delta I hash theta n minus 1. So this is a sum from I is 0 to n minus 1 to the I, and then you're doing U hash and delta I hash, so that's okay. Okay, but then let's think about to what's the subdivision of the boundary of U. Okay, so that's the sum minus 1 to the I, the subdivision of U composed of delta I, which is sum minus 1 to the I, U composed of delta I, hash of theta n minus 1, because we're subdividing n minus 1 chains here, so you take the map and you apply it to theta n minus 1, and that's the same. Okay, so now we see that the subdivision commutes with the boundary operator, In other words, subdivision is a chain map. The next kind of key point we're going to need is to show that it's not only it's a chain map, so it gives you a map from the homology of X to the homology of X. But that map's just the identity, it turns out. And the reason it's the identity is because this subdivision chain map is actually chain homotopic to the identity. And we proved earlier that if you've got two chain maps that are chain homotopic to each other, then they have the same effect in homology. So that's the next key thing we need to prove, that subdivision is chain homotopic to the identity, but that'll be in the next video.